Hello friends, welcome to YouTube channel Tech Guru Gautam Prasad. This video is on synchronous motor. So let's explore synchronous motor. AC machines, it is a part of AC machines. So let's first introduce synchronous motors. Synchronous motors are widely used in the industry for high precision applications. And this motor runs at constant speed, that is its specialty, and it does not depend on the torque acting on it. So it has a constant speed torque characteristic, and the efficiency of the synchronous motor is around 90 to 93%. So friends, in this figure, I have tried to show you the torque speed characteristic of the synchronous motor. As you can see, it can run only on the synchronous speed, and it cannot run if it is not running at the synchronous speed. So there are two possibilities: either it will run at synchronous speed or it will not run at all. So the slip in this case is 0%, uh, and it is running at synchronous speed. As you can see here, here it is. This is the line of the constant speed, and this is the rated torque line, and this is the pull-out torque line. Pull-out torque is a torque where this motor pulls out of synchronism and stalls. Basically, it stops running. So, friends, synchronous motor is a doubly fed motor. Three-phase supply is given to the stator of the synchronous motor, while the rotor is fed from DC source for excitation of the field winding. So friends, here in this picture, the construction of the synchronous motor has been shown. As you can see, the stator has got three-phase winding, two-pole three-phase winding basically, and the rotor has got a DC winding, which is creating two poles here as well. So you have got a field winding with DC supply, and a stator is there, and a stator winding are placed in the slots of the stator, and it is fed with three-phase supply. So there is no constructional difference as such between the synchronous motor and the synchronous generator. In fact, you can operate synchronous motor as a synchronous generator also. The difference is that you will require a prime mover for the rotator to rotate, and when rotating, this three-phase winding on the stator will start generating EMF, three-phase EMF. So that is how this synchronous motor can be operated as a synchronous generator. So friends, a stator has a laminated core with slots to hold the three-phase winding on it, and the rotor holds the field winding. The rotor comes in two constructions. One is called salient pole type of the construction, and the other is called cylindrical pole type of the construction. Synchronous motor is likely to hunt when you demand more than the rated torque, and hunting is a situation when rotor pole falls back the stator pole when it is running, and this is a situation when it starts oscillating towards the across the mean position of the center line of the stator and the rotor. So basically, this situation must be avoided, and it is avoided with the help of damper winding placed on the rotor poles. So a damper winding is nothing but damper. It is the presence of the damper bars on the tip of the rotor poles, and they are kept shorted on either side of the face, basically, and this helps the synchronous motor to avoid damp hunting. So friends, when the stator is fed with three-phase supply, uh, it is given to the stator of the synchronous motor, and it produces rotating magnetic flux of the constant magnitude, rotating at the synchronous speed, like it does in the case of the induction motor. So the rotor has been shown in this picture, and these two slip rings, help us in feeding DC to the rotor winding, and this DC helps in giving excitation to this rotor winding, and the DC supply on the rotor will also produce a flux of constant magnitude. A three-phase synchronous motor is not self-starting. This is noteworthy. This must be understood. It needs some help, to make it reach to the synchronous speed somehow. And then, if you switch on the field excitation of the rotor, then it gets locked with the synchronously rotating, stator field, and then it keeps running at the synchronous speed. But it needs some help. The rotor needs some help to make it reach to the synchronous speed or nearby speed. If the rotor of the synchronous motor is rotated by some external means at the start, it will keep running at the synchronous speed. So, friends, in this slide, I have tried to show you synchronously rotating stator field. So here, the stator winding is there on the periphery of the stator, and these stator poles are rotating at synchronous speed. So basically, you can see these cross are showing uh, the current is getting into the piece of the paper or uh, in a direction inward from the uh, screen, and these dots are showing you the current coming outward of the screen. So these two directions, as the changing direction of the current is, changing the nature of the pole. So once this stage is reached, that when your rotor has been rotated to a synchronous speed or nearby synchronous speed, and you switch on the field DC power of the field, and then it gets locked to the synchronous speed with the stator rotating poles, at this, and it keeps running at the synchronous speed then after. So this is a four-pole synchronous motor, and synchronously rotating stator field of the synchronous motor has been shown in this picture. So friends, now let's discuss methods for starting the synchronous motor. The different methods that are generally followed to start the synchronous motor are as follows. First, by using a pony motor, that is a small induction motor. Second, by using a damper winding. Third, by using a DC motor. And fourth, starting a synchronous motor as an induction motor first. So, starting methods for the synchronous motor by using a pony motor. In this method, the rotor of the synchronous motor is brought to its synchronous speed with the help of an external induction motor. And this external motor is called pony motor. So, when it reaches, we switch on the rotor DC power so that the field excitation takes place, and after the field excitation the rotor poles gets locked with the stator poles, and it keeps running at the synchronous speed with the synchronously revolving stator field. Now, a starting method for the synchronous motor, here we are going to discuss by using a damper winding. So, damper winding has been shown here, as you can see in this picture. These are the damper windings. These are bars. Basically, these bars are passed through the pole tips, and the pole tips, and this is the end ring with the help of which, a portion of the ring has been shown. This is not round, but this portion of the ring is used to, short circuit these bars so that it acts as a, kind of squirrel cage induction rotor. So basically, these windings are short circuited at both the ends with the help of end rings, and thus forming a squirrel cage system. So here also this rotor has been shown, and the damper copper plates are shown. These are damper bars copper plate to short circuit these, bars. And these are the slots basically in which the DC winding is placed. Now let's discuss the next method by using a damper winding. So now when a three-phase supply is given to the stator of the synchronous motor, it starts, as a three-phase induction motor in the beginning, and then when it reaches to a nearby synchronous speed, then we switch on the DC supply of the rotor, and the rotor then starts rotating at the synchronous speed when it is locked with the stator field. So here the construction of the rotor has been shown in a bigger picture. These are the damping bars, basically damper bars or damping bars are the same thing. And this inner ring is the short circuiting ring. Basically, there is a single ring that has been used to short circuit all these bars, and this helps the rotor to start as a induction motor in the beginning, and then when it reaches to the nearby synchronous speed, we switch on the DC supply of the rotor. So the next method is by using a DC motor. This is, DC motor helps the uh, synchronous motor to reach to the nearby synchronous speed, and then again we switch on the rotor supply, DC supply at this speed of the rotor, and then the rotor poles are getting locked with the stator poles, and then keeps running at the synchronous speed. So starting as an induction motor, the synchronous motor is started as a synchronous cage induction motor, and when the synchronous motor is started as a slip ring induction motor, the three ends of the winding are connected to an external resistance in series through the slip rings. So here the slip ring induction motor is starting the synchronous motor basically. So power angle of the synchronous motor must be understood when we are discussing the synchronous motor. The synchronous motor at the synchronous speed runs at the synchronous speed, but increase in the shaft load causes the rotor magnet to change its angular position with respect to the rotating flux of the stator by an electric angle delta. And this angle delta is called power angle, load angle, or torque angle. So these are the three names of this angle: power angle, load angle, and torque angle. You can call it by either name. So here is the stator and the rotor. A stator pole and rotor poles are perfectly aligned with each other at no load condition. But when it is loaded, basically with the increasing load, this rotor starts falling back in the position with a small angle, particularly, basically it is delta. Here it is shown as alpha. Alpha or delta is the same in this case. So here it is again delta. So this is the angle, a small angle of falling back of the rotor poles behind the stator poles. And this angle is called load angle or power angle or torque angle basically. And with the increase of the load, this angle also increases. So this is a plot of the armature current. Armature current is nothing but the stator current, and the field current of the synchronous motor is known as a V curve. So these are like V shapes. That is why it is called V curves. So for the lagging power factor, as you can see, this is the line of the unity power factor and at unity power factor you can see the armature current is least, and before that also in the case of the lagging power factor armature current is higher, and as you are reaching to the unity power factor, this armature current keeps on dropping, and with the field current. Basically, field current is increasing in this direction, and field current, this armature current is increasing in this direction. So as you are studying it for a particular load, basically, so when you drop the load, basically it goes on dropping for a particular excitation of the rotor. So here, this is quite obvious that this synchronous motor can operate in all the three power factors: lagging power factor, unity power factor, and leading power factor. So when it operates at unity power factor, you call it the normal excitation. So normal, under the normal excitation condition, this motor, synchronous motor, operates at unity power factor, and for under excitation it operates at lagging power factor, and for over excitation this synchronous motor operates at leading power factor. So this is a very unique kind of the motor that is capable of operating in all the three power factor zones: unity power factor, lagging power factor, and leading power factor. So this bottommost curve is no load curve. This middle one is for the mediocre uh, level of the load, and this topmost curve is for the full load curve. Let's proceed. So the plot between the power factor and the field current of the synchronous motor is called inverted V curve. That was a V curve, and this is an inverted V curve. So inverted V curve is plotted between the power factor and the field current. So V curves are plotted between armature current and the field current, but this one is plotted between power factor and field current. So you can, as I told you, that you can operate this synchronous motor in all the three power factors, lagging power factor, unity power factor, and leading power factor. So as you increase the excitation from a particular level, you will see the change in the power factor of the motor. Basically, the power factor uh, meter is connected in the stator circuit, and when you change the excitation, you will observe that your power factor is changing from lagging to leading. In between somewhere, you will come across the unity power factor. So that is a very nice scenario to observe, to be observed in the case of uh, synchronous motor, and this is a practical that must be done, and you can see it practically if you have a synchronous motor in your laboratory. So what is hunting in the case of the synchronous motor? At no load, the magnetic axis of the stator and the rotor coincides as the load angle delta is 0. However, when the motor is loaded, the rotor axis lags uh, the stator axis by an angle delta. And if the load is suddenly changed, mind it, when it is suddenly changed, the rotor will not immediately attain its equilibrium position, but pass beyond it. That means it uh, uh, eh, in the place of stabilizing at a particular position, it crosses the boundary and starts oscillating between the across the mean position. So this is called hunting position, and it creates noise, losses, and many other kind of the mechanical damage to the motor. So this must be avoided. So this periodic swing of the rotor on either side before stopping at the equilibrium position is called hunting in the rotor. So it has to be loaded carefully when mechanical load is applied on the synchronous motor. It has to be loaded carefully, and it has to be taken care of so that hunting does not take place, because it has got numerous losses in terms of mechanical losses, bearing losses, eddy current losses, power factor. In terms of power factor, there are numerous losses that you come across. And let's explore what are the causes of hunting in the synchronous motor. And the first cause is sudden change in the load, and second cause is sudden change in the field current. Third cause is a load containing harmonic torque. Load containing means load itself is containing harmonic torque. And the fourth reason is the fault in the supply system. Because of the fault in the supply system, also sometimes the synchronous motor starts hunting. So the effect of the hunting in the synchronous motor are as follows. It may lead to the loss of synchronism. That means the synchronous motor will go out of the synchronism and it might stop or stall at all. Second is that it produces mechanical stresses on bearing, on windings, on whatever mechanical components you have in the motor. Third is increase in the machine loss or causes the temperature rise of the windings. And fourth is causes greater surge in the current and power flow. So this is again damaging in the power system on which your synchronous motor is operating. A reduction of the hunting in synchronous motor. First, by using damper winding. Damper winding damps out the hunting by producing torque opposite to the slip of the rotor, and the magnitude of the damping torque is proportional to the slip speed. And second method, by using flywheels. By providing large and heavy flywheel to the prime mover, its inertia can be increased, and which in turn helps in maintaining the rotary speed constant. So flywheels are meant for that only, for maintaining the constant speed, so that when it tries to reduce, it supplies the extra amount of the torque needed to keep the speed constant. Application of the synchronous motors are also important. The first application of the synchronous motor is that having no load connected to its shaft for the power factor improvement. So on no load, it can be used as a synchronous condenser. So basically, for the power factor improvement of the line, it is this synchronous motor is used, and that's a vital use of the synchronous motor. The second is that synchronous motor finds application where the operating speed is less and high power is required. So speed is less and high power is required. There, the synchronous motor has got a vital application. Third is that as the synchronous motor is capable of operating under either leading or lagging power factor, it can be used for power factor correction. And the synchronous motor under no load with leading power factor is connected to the power system uh, this this static capacitor cannot be used. So application of the synchronous motor, it is used in the rolling mills, it is used in chippers, it is used in mixers, it is used in pumps and compressors as well. So these are the different applications of the synchronous motor. So friends, thank you very much. If you liked the video, don't forget to like this, give a thumbs up so that the moral of making the video boosts up. And if you want to ask any question, my friend, do write in the comment box. I would like to reply your question as early as possible. If you have some friend with which it will be useful to share, do share this video with them. And if you are not subscribed yet, I would suggest you to subscribe to this channel so that you keep getting this type of useful videos. So thank you very much. Till the next video. Thank you so much.